Hello, everyone. Hi, Algebra 2. Whenever you're watching this, good morning, good evening, good afternoon, whatever it is. So, today's going to be my first lesson that is going to be new material. I know last class I had you do something old to kind of get comfortable with it. So, this was the lesson that we were getting ready to start. We were getting ready to start chapter 7. To give you an idea of how I'm going to conduct virtual lessons, I am not going to try to do the same amount of material that I did on a daily basis with you. So, what I think is going to make the most sense is if I can take a topic and split it up over the course of the 2 days that we meet. So, Monday, Thursday for white classes or Tuesday, Friday for blue classes. Then I feel like you're getting valuable information in short, easier to understand chunks rather than trying to throw a lot of things at you when you're not right in front of me where I can help you. So, the topic that we're starting, chapter 7, the very first section, ironically, is exponential growth and decay. So if you're the type of person that will learn math and say, when am I ever going to use this? This is one of those topics that up until about 6 weeks ago, you would have probably thought you were never going to use this. When I would teach things with exponential growth, I would talk about things like colonies of bunnies rapidly reproducing and growing exponentially. I never thought I'd be talking about a virus, but that's where you've heard it recently. When they talk about something like the spread of coronavirus growing exponentially, it's because it is constantly having a multiplier. For example, you might have read articles in the news that say that the number of cases they expect to double every day. When I multiply by 2, I am growing exponentially. I would say that I have a growth factor of 2 because every day I multiply by 2 again and again and again. That's called an exponential function. Exponential functions can either grow really, really rapidly or they can drop really rapidly. So you see almost like a really steep curve going through. I don't know why that's on my screen. Get rid of that. So really steep curve going up or a really sharp drop going down is an exponential growth or decay. So what we're going to start with, I'm not going to have you do the warm up, fill in the tables. Instead, I'm going to show you how we can do that together on your calculator. So first, what an exponential function is as far as what it looks like. We know what linear functions look like. We know what quadratics look like. An exponential function is going to have an exponent that is a variable. So the general form is called ab to the x power. This is not really written correctly. This x is an exponent. The base number, so looking at this first example, this b value, we call it the base or the constant. That number that has the variable exponent, that is your multiplier. So 2 to the x power is actually saying something is doubling over and over and over again. So that's an exponential function. So what I want to do, a couple things. I want to show you how to create these tables that are filled in on your calculator. I want to show you how to create the graphs on your calculator. And then I want to talk about how do you know whether it's growth or decay without ever having to grab your calculator. How do you know some of the key features of the graph without having to be relying on your calculator? So what I want you to do now is I want you to grab your calculator. If you have it in another room or somewhere else, pause this video, go find it. If you have it close by, grab it, come back. And I'm going to be doing everything on this calculator. That link that I sent out using your graphing calculator should work now. The tech department said they fixed it. So if you don't have a calculator at home, you can use the one that's on your Chromebook. So here's what you're going to do. You're going to go to the y equals button. And what I want you to do on your y equals, just some housekeeping things. I want to make sure that nothing is on. So all your plots should be off. If one of them is on, go on top of it and hit enter. Make sure there's nothing in your y equals. From there, we're going to graph this first one, this 2 to the x power. So you're going to hit a 2. You're going to hit the exponent button. And then you're going to hit the x button. So that's getting you 2 to the x power. I don't know the last thing you graphed on your calculator, so I want you to hit zoom 6 to get a basic window. You can hit 6 on your keyboard, or you can just hit 6 using your calculator. And you will see very slowly, sometimes takes a little while on this calculator compared to the ones we used in class. You can see this graph that looks like it's right along the x-axis, and then it takes this really, really sharp turn. That is an example of a growth graph because every single x value is causing it to double in y value. So that constant doubling feature. If you ever have to fill in a table and you don't want to do it individually, like button by button on your calculator, the calculator will actually do a table for you. We haven't done this in a while. So to get to your table, you're going to go to second and graph. That's your table feature. And I don't know where it'll start. It might start somewhere different than 0. This calculator is pretty new as far as I just got this app, so it's starting at 0. But you can scroll up and down and it will give you different values. So what this is giving you is it's giving you an XY table. So if you look at the one that's on the notes that I have here, if you put -4 in, you get 0.0625. And then if you put -3 in, you get 0.125. And then -2 in, 0.25. And then you can start to see it go up. Once we get past 1, 2, 3, you start to see these bigger and bigger numbers. And you can actually see how quickly it begins to grow if you go even further out than the table. So you're in the hundreds by 7, you're in the thousands by 10. So that's an example of an exponential growth graph. Very easy to graph on your calculator. If you're not sure if it's a growth graph, you can use your calculator. I want to spend some time in the next few minutes giving you an idea of how do you know if it's growth, how do you know it's decay, just by looking at the equation, so you don't have to be as reliant on your calculator. The other thing that I want to talk about is where it crosses the y-axis. That's going to be a question I ask a lot. So where it crosses the y-axis on the table, where it crosses the y-axis will be whatever value goes with the 0 in the x column. So if I have 0 for my x, 1 for my y, that's your y-intercept. That's the place where it crosses the y-axis. I'm going to talk a little bit in a second about other ways to know it without a table, without a calculator. But if I ever ask that question, that's what I'm looking for. If you look at this next one, close this so you can see it. So this is an example of one that's going to be a decay graph. Here's how you can tell if it's a decay graph, and we'll continue to talk about this. If the value that's being taken to the x power, if that base number is less than 1, it's going to drop. It's going to get smaller because instead of multiplying by 2, for example, you're multiplying by a third, which is going to make it smaller and smaller and smaller. So your expectation is that your graph is going to have this sharp decline. It's called a decay graph. On your calculator to do this, you're going to go to y equals again. You're going to get rid of the one we just did. It does help to use parentheses with fractions. So you're going to do parentheses 1/3, close your parentheses, hit the exponent button. And again, x is your exponent this time. And if you hit graph, I don't know how quickly it'll graph it here. This calculator definitely graphs slower than the ones I'm used to by hand. So there you see this really steep decline. Same thing though, it looks like it almost meshes right into the x-axis right here. If I want to fill out a table, I can again go to second and graph, and I get that table look again. And I can go up and down if I want to toggle to different numbers. So it starts off really high. At -4, you get 81, and then it drops, and then it drops, and it keeps dropping. And before you know it, you're into numbers smaller than 1 very quickly, and really, really small numbers. Eventually it gets to the point where it's writing it as a scientific notation because it's so small. Again, your y-intercept is where x is 0, so your y-intercept would be 1 again. And then you see that really sharp decline. The last one here, it has an extra number in front. That's called the a value. We're going to talk about that as we go through. This is still your multiplier, your number that has the variable exponent. So 3 is your multiplier. So if I want to graph that, I expect that this is going to grow because it has a multiplier or a base number bigger than 1. This graph is actually going to triple. So I'm going to put the fraction in parentheses. Or was it 1/2? I believe, sorry, 1/2. And then times 3 to the x power. Make sure I typed it in right. 1/2 times 3 to the x power. 1/2 times 3 to the x power. Hit graph. Again, the graph this time, it looks like it starts right along that x-axis, and then it takes a really sharp growth right after it goes through the y-axis. I can look at the table, second graph, and I can see values before 0. And then when I really see that growth kicking in is after I get past 0, and you'll see by the time you get to 7, you're already in the thousands. That is an example of exponential growth. That would be one that the growth factor is 3 because it's tripling. Your y-intercept is right here. It's the 0.5. The way you can tell that without looking at your table, it's going to be your a value. It's going to be whatever number is in front of your base number. In this case, this didn't have a number in front. So we say that the a value is just 1 because when I multiply by 1, I don't have to show it. This is going to have an a value of 1/2. So that is your y-intercept, and that is always true. You can always use your calculator if you don't remember that. So we have two different types of models that we've looked at. We have exponential growth and exponential decay. Obviously, growth is going to show that really sharp incline, and decay is going to show that sharp drop. And you can tell by just looking at the equation. You don't have to graph it on your calculator. One feature of this graph that is brand new is a fun word to say. It's called an asymptote. The P is silent. It's not an asymptote. It's an asymptote. An asymptote is something that if you take pre-calculus, you'll actually spend a lot more time on. An asymptote is a line that the graph gets really, really, really close to, but never actually touches. Often you'll see the asymptote on a graph written as a little dotted line, almost like a barrier line. What's going to happen with these graphs? These graphs are going to get incredibly close to the x-axis, to that y=0 line, but never actually touch it. And that's true for all of the exponential functions we're going to work with. They're always going to have an asymptote on the x-axis, or you could call it y=0 if you prefer. So to kind of summarize what I just went through, here's your basic exponential growth model, a b to the x power. A is going to help you find your y-intercept. It's going to be where it crosses the y-axis. B is going to be your growth or decay factor. That's how you're going to tell if it's going up or down. This tells you how you can tell. Obviously, you always can use your calculator if you're not sure. If your b value is bigger than 1, so 2, 3, it could even be a decimal. It could be 1/2, a 1.5, or 5/3. Anything that's bigger than 1, that's going to be a growth graph. Anything that has a b value that's between 0 and 1, so a half, a third, 0.5, 0.2, those are going to be decay graphs. Continuing to summarize, whatever your a value is your y-intercept. It's going to be where you cross the y-axis. Your domain's everything, so you can use the all real number symbol or you can just write it. Your asymptote is always that y=0 or that x-axis. And your range is how low and how high it goes, is always above the y-axis. So it's everything bigger than 0 for all of these graphs. Going through here, and this is kind of where I want to stop today. I'm going to have you do, I didn't really love the exponential growth questions on Delta Math. I may be able to find a few. I think I'm going to create a Google form that just kind of takes you through some of these, identifying, is it growth, is it decay, what's the y-intercept, some of the key features without going through and having to do too much in the way of graphing. So looking at these four, and I put a fifth example when I did this, you should be able to look at this and know whether it's growth or decay just by the equation, not have to go to your calculator. So for example, this first one, your growth or decay factor, that B value is 0.95, smaller than 1, so we say it's a decay graph. Now it's not going to decay as much because you're just under 1. We would say this would be like a 5% decay because it's only 0.05 under 1. This one will be a growth graph. This was like the first one we looked at because your B value, your base value is 2. So this is one that is doubling every single day. This is also a growth. This was even a sharper growth because it's quadrupling every day or every hour or every year, whatever you're working with. So that's a growth graph. This one right here with the 0.75 base, that's a decay. Again, that one's going to decay a little sharper than this first one because it's actually going down by a 25% drop. And then this last one that I added on at the end, that's also a growth because 1.5 is bigger than 1. The other thing I want to mention is the y-intercept, so you're comfortable with that. This one would have a y-intercept at 0.12. This one will be at 0.25. This one will be at 0.3. This one over to the right would be at 0.11. And this bottom one would be at 0.3. So I know all of that. I know all of them have a domain of all real numbers. I know all of them have a range y greater than 0. I know all of them have an asymptote at y=0. So those things I know for sure. And it's really just the growth and decay and the y-intercept that change. Everything else that I'm going to do here, all the real life examples talking about having money grow or having some particular idea either drop or grow, I'm going to save that for the next lesson. Biggest thing I want to make sure you're comfortable with is you can grab your calculator, you can graph these, you can fill in a table, you can identify growth versus decay and all the key features just by looking at it, and you have your calculator as your backup plan if you need to do that. So hopefully this helps kind of go through the overview. I will also post a short assignment that goes with it just to check understanding. As always, if you have any questions, please just let me know. Reach out to me via email, shoot me a message on Classroom. I can have some Google Meet sessions so we can talk. But I'm here if you have anything that you need answered or you just miss that math connection and wish you were sitting back in A115. So I'll talk to you guys later. Have a great day, night, afternoon, whatever it is, and let me know if I can help you in any way.